Good afternoon, everyone. How are you?
I'm good, thank you.
Good. The plan today is to cover sections 2.1, 2.2, and 2.3. Not everybody has taken the test yet, so we're going to delay reviewing that for a bit till we get everybody having taken it. So 2.1 has to do with complex numbers. And this is going to be a review, I think, for most of you, because complex numbers have been covered in previous math courses here at Bellevue College. Math 97, 98, 99 all cover this as well. So hopefully it will be sort of a review for some of you, maybe all of you, who knows. And the objectives for today, we want to be able to add and subtract complex numbers. And we will be defining what a complex number is and what it looks like, but we want to be able to add and subtract. We want to be able to multiply and divide complex numbers. We want to be able to perform the square root of a negative number. We might have equations that when we go to solve them, we're looking at a negative number and we may need to take the square root of that. So we need to have a method of doing that. And the mathematicians have come up with a way that they can do that. And then we want to be able to solve quadratic equations with complex imaginary, if I can spell that properly, solutions. So we want to be able to solve quadratic equations that have complex imaginary solutions. And we'll talk about each of these items in depth. So let me just give you a definition first. If we have the situation where we have to take the square root of a negative number, maybe the square root of 4 is something we need to take the square root of. So what the mathematicians have done is divide this into the square root of -1 times the square root. Well, I'll just put it both under the same root and the square root of 4. So I could say square root of -1 times the square root of 4. And then we give this a definition. And we say, let the letter, small letter I, equal or be defined as the square root of -1. So we would have, this would be I root 4. We'll replace the square root of -1 with an I. And we'll say, well, that's I root 4. And then we can take the root of 4 and say, well, that could be plus or minus I 2. Okay, so in general, if we're talking about complex numbers, a complex number has a real component and an imaginary component. And the general format, the real component, is called A by convention, and the imaginary component would be B, I, and we might let the complex number be represented by a value z, for instance. So we might say z equals a plus bi, where z, being a complex number, is really made up of a real component. That is to say, this value exists on the real number line, and this value does not. This value exists only in the imaginary axis. Okay, and we're going to go through some additional examples on that. But that's generally how we're going to define a complex number. Now I'm going to stop right there before I jump into some examples and manipulations and problems, and see if there are any questions at this point on what we're going to cover, our objectives, and then talking about complex numbers and real components and imaginary components. Any questions on that stuff at all?
I have a question real quick.
Sure, go right ahead.
So the whole expression that you did above of I2 or plus or minus I2, that is the whole imaginary number, not just the I, right?
The I is the imaginary portion.
Okay.
So that would be this portion here. That would be the bi, where b would be plus or minus 2, and then I would be on the imaginary axis.
Okay, so is that expression a complex number or just an imaginary number?
This is the imaginary component
Mhm.
of a complex number.
Okay.
This is just the imaginary component,
Okay, cool.
as discussed here.
Mhm.
And then the a is the real component, which exists in the real number line.
Mhm.
Now, either a or b could be 0. If a were 0, then it would be a pure imaginary number. If b were 0, it would be a pure real number. But if we have a real component and an imaginary component, then we're going to say, well, that's a complex number. And we can draw the axis looking like this, where the horizontal is the real axis and the vertical is the imaginary axis, which I might label I. And again, here's the origin. Now this z value, we're going to go into this z value, then if we went out here distance a and went up here distance b, then we would have a point out here on the imaginary real, the imaginary axis, that says, well, here's a point at a plus bi, and if I extend a value from the origin to this point, I can say, well, this value represents the complex number. This would be z. So the complex number equals a plus bi, as shown here. Okay, and we're gonna get into that in more detail. I just want to give you a little bit of an overview of what we're going to be looking at. Okay, other questions? Feel free to ask questions. Okay, so let's go ahead and do some work with complex numbers. Let's say I have complex number z1, and it looks like, let me move this camera just a little bit here. Let's see, make sure you can see that. Let's say I have complex number z1 that is 1 plus 2i, for instance. A is 1, b is 2. And I might have complex number 2, which is z2, and it's maybe 1 minus 2i. And we say, well, we talked about adding, subtracting, multiplying, and dividing. Well, let's try it. Let's say we have some imaginary numbers here. So if I were to draw these on my real and my imaginary axis, if I go over 1 and up 2, then I have a point here at 1 and plus 2 in the I direction. So that represents z1 as I've shown it here. And then z2 would be over 1 and down 2. So I could say, well, I have a point here at 1 minus 2i. And if I extend from my origin, I could call that z2. Okay, and now let's go ahead and do some arithmetic operations. Let's say we want to add z1 plus z2. So z1 is 1 plus 2i. z2 is 1 minus 2i. And we add these like we do any binomial. We add the like parts. So 1 and 1, that gives us 2. And plus 2i and minus 2i, combine those, and those cancel, don't they? So there's nothing there. So now z1 plus z2, if that equals 2. So I go out here, 1, 2. So z1, this complex number, and z2 complex number, when I add those together, you'll notice what happens. The real part of z1 is out to here, and I add the real part of z2, which is another one that takes me out to here. And the imaginary component, the positive 2i and the negative 2i cancel. And so we end up with a value of 2, and it's on the real number line. That makes sense to everybody, what we get there, how we get that 2.
Could you explain how you did the graph and then why like it's like that?
Yes. Here's my first point, 1 over 1 and up 2. So keep in mind, the horizontal axis I'm calling the real axis. And the vertical axis I'm calling the imaginary axis, which I'll label as I. So if my Z1 complex number, and if I'll say this is a complex number, and it's complex because it has a real component and an imaginary component. That's what makes it a complex number. So I plot that value, 1 plus 2i. Here's 1, and then 2 in the I direction. So that gives me this point right here. And if I draw a line from the origin to that point and call that line Z1, then that represents complex number Z1. And I could draw another line down here to this point, and that represents complex number Z2. So I've got this value and that value. And then I can do arithmetic operations, add, subtract, multiply, divide, take absolute values. And we're going to take you through those examples. But this is what we're starting with. And here is my first example, just adding Z1 plus Z2. Questions?
It's basically the 1 plus 2i or the 1 minus 2i. That's like x and y basically. You said like you went 1 and then up 2 or down
Well,
2.
don't think of it as x and y. Just think of it as a horizontal axis as the real axis.
Oh, okay.
And the vertical axis as the imaginary axis.
Oh, okay. And you point out that like
yeah, here's real.
1, 2 is real, 1's imaginary. Okay.
1 in the real direction and 2 in the I direction.
All right, got it. That makes more sense. Thank you.
Sure. Now we could also subtract. So if I subtract, I could say Z1 minus Z2. And I could say, well, Z1 is 1 plus 2i, and Z2 is 1 minus 2i. Now, if I'm going to subtract this value here, then I'm going to have to change the signs, aren't I? I'll change the signs. So I'll change that to a negative, change that to a positive. Okay, so when I do that, these ones cancel, don't they? If I'm subtracting, the ones are going to cancel. And now I have 2i, and I'm subtracting a 2i. So because I'm subtracting a negative, it turns into a positive. So that gives me a positive 4i. This is just the same kind of operation you would do with any kind of numbers. You're adding and subtracting. Here we're just subtracting. Okay, so we end up, if I want to call Z3 equals Z1 minus Z2, I could say, well, Z3 equals 4 in the I direction. So I could go 1, 2, 3, 4. So there's 4 in the I direction, and Z3 would be a value that went from the origin up here to 4. Okay, 4 in the I direction. Okay, see what we've got here. So we're letting these z values be the complex number. Now we could also multiply. So I could say z1 times z2. And let's see, z1 is 1 plus 2i. And z2 is 1 minus 2i. And we can combine those just like we combine any binomial. So I could say, well, I'm going to first, outer, inner, last. First times first is 1. Outer is negative 2i. Inner is positive 2i, so those cancel. And last times last is a negative. 2 times 2 is 4, and I times I is I squared. So we have 1 minus 4i squared when we FOIL it. And then we have to simplify. Always simplify. In fact, I'm going to mark that in red to make sure that we always want to simplify. So this says we have 1 minus 4 times I squared. Well, that's I times I. And remember what I was defined as, I equals the root of negative 1. So if we square that, we get just negative 1. So this turns into 1 minus 4 times I squared, which is negative 1. So that's 4 minus minus is a plus. So 1 plus 4 is 5. Okay, make sense to everybody? Questions? And we can also do a divide. Let's say we do a divide. Say we divide z1 by z2. z1 was 1 plus 2i. z2 is 1 minus 2i. And so in the denominator, we have this I value, and what we're going to do is remove that. Remember, its I represents the root of negative 1. And we don't want radicals in the denominator, do we? So just like we always remove radicals from the denominator, I'll remove it by multiplying by the complex conjugate. Complex being, it's a complex number, a plus bi, and the conjugate being the opposite sign. So we'll multiply this value by 1 plus 2i, and also the numerator 1 plus 2i. Whatever we do to the denominator, remember we have to do to the numerator. So this is called the complex conjugate. Okay, so that's the mechanics. Now let's just go ahead and complete this. So we multiply the denominator. We FOIL that 1 plus 1 times 1 is 1. Outer and inner cancel. And we multiply here, we get a negative 4i squared. That's what we had above, wasn't it? And we call that 5. Okay. Now let's take a look at multiplying the numerator. We FOIL the numerator. 1 times 1 is 1. Plus outer is 2i. Inner is 2i. So that gives me a 4i. And then last is plus 4i squared. Okay, so the 4i squared, well, that's going to be negative 4, isn't it? So that's going to give me 1 plus 4i, and then this becomes negative 4 times negative 1. I squared is negative 1. So I'll leave this positive and get the negative out of here. So I have 1 plus 4i, and then 4i squared. I squared is negative 1. And then we want to simplify. So we get this 1 And this -4, that gives me -3 plus 4i over 5 in the denominator. And then because I'm going to put it in the form of z equals a plus bi, I'm going to put the -3 over 5. So I'll get -3 over 5 plus 4i over 5. So that we have a plus bi, where a is the -3/5 and b is the 4/5. Okay, so when we do the multiply, when we do the divide, we're doing a divide here, we end up with the answer of a plus bi, which in reality looks like -3/5 plus 4i, or 4/5 I. Questions? Okay. The next thing I'd like to do is take the absolute value. So the absolute value, that's a function on our calculator, isn't it? Which says I want the absolute value of some, in this case, complex number. So if I say I want the absolute value of z1, and z1 looks like 1 plus 2i, and we said, well, 1 plus 2i, 1, it looked like this. Here's z1, and it's 1 plus 2i. Here's the real, here's imaginary. This is a right angle. And so what I'm looking for with the absolute value is the length of this complex number. I can call that a complex number. Looking for the length, I could also call it a vector. I could say it has magnitude and direction. The magnitude is the length. The direction is where it's pointing away from the real axis. Could be pointing any direction around here. So if I call this a vector, it's magnitude and direction. And if I'm looking for magnitude, then I want to find the length. And I know the length of the small side here is 1, and the length of the longer side here is 2. So I can find z1 equals, and I can say, well, that's Pythagorean theorem, 1 square plus 2 square. This side squared plus this side squared equals this hypotenuse squared, but I don't want the square of the hypotenuse. I just want the hypotenuse itself. So I'll take the square root of each side. So that says I have 4 plus 1 is 5. So I'm saying the length of z1 is the square root of 5. Now, if you're asked this as a question, then you'd say, well, do you want the exact answer? This is the exact answer, isn't it? If it says I would like the answer to 2 decimal places rounded, well, then you're going to grab your calculator and say, well, let's see, what's the square root of 5? And it's 2.236067 and a few other decimals. And if you're asked for it for 2 decimals, you'd say, well, z1 to 2 decimals is 2.2. That's a 6, so I round that 3 up to a 4. And I would say, and instead of saying equal, I'm going to say approximately equal with this wavy line here that says z1 is approximately equal in magnitude to 2.24. And exactly the magnitude would be root 5. Okay, so I could say, well, the magnitude then represented this way is 2.24 rounded, or root 5. Questions?
Could you please explain why it's 1 squared plus 2 squared?
Yes, because we were looking at this triangle right here. We said that the complex number z, which is this value here, is 1 plus 2i. So that's a plus bi, where a is 1, b is 2. So here's 1 along the real axis. Here's 2 along the vertical or imaginary axis. So this becomes a right triangle, and we're looking for the length of the hypotenuse. And the length of the hypotenuse is the square root of this side squared plus this side squared. Have you heard that before?
Yes. Thank you.
Pythagorean theorem. Okay.
Thank you.
Yeah. Other questions? Okay. So we've done an add, a subtract, a multiply, divide, an absolute value. We could also take the absolute value of a product, say Z1 times Z2. So let's see what that might look like. So we have Z1 times Z2. Well, absolute value of Z1 up here was √5. And I guess we didn't do Z2. We could do, well, let's just say we want to do Z1 squared, just make it without having to redo everything. Say we want Z1 times Z1. So absolute value Z1 is √5. If we multiply √5 times √5, we get 5, right? Another way of looking at this, if we take the radicals out of here and make it an exponent, we could say that's the same as 5 to the 1/2 times 5 to the 1/2 power, right? The square root in exponential form is 1/2. So 5 to the 1/2 times 5 to the 1/2, we have a common base of 5. So we can add these exponents, can't we? So that's 1/2 plus 1/2, or 5 to the 1, which is just 5. Okay, so that's what we get if we take the absolute value of the product. Questions on that one?
I have a quick question here. So, taking the absolute value of a complex number.
Can you speak up a little bit, Gopal? I can't quite hear you.
Okay. So taking the absolute value of a complex number, what's the difference between that and what we were doing earlier?
Earlier today,
Yeah.
this here.
Correct. Yeah.
Same thing, just with numbers. We're just putting in values now. Same idea. We're now just putting in numbers.
Okay.
So we have the absolute value of a product. How about we do the absolute value of a quotient? Let's see what that looks like. All right, so the absolute value of a quotient would be absolute value. So I could put Z1 over Z1. And I could say, well, that looks like √5 over √5. Well, that's just going to be 1, isn't it? We have the same value in the numerator as the denominator. That's just 1. So the absolute value of a quotient is 1. The absolute value of a product we came up with is 5. So now we've gone through adds, subtracts, multiplies, and divides. And we've done them all algebraically. Now, I'm also going to show you then that we can do them graphically if we have, say we have a real and an imaginary that looks like that. And we might go out here, 1, 2, 1, 2, 3, 4. And I might have something that goes to here, as we had before, 1 plus 2i, that was this vector. And I had a vector out here that was 1. So here's 1 plus 2i, and here's 1 minus 2i. And when we added them together, we got 2. If we were to add these together, we just get 2, don't we? Because the imaginary values cancel. So if we add them together and call it Z3, then we get something out to here. We could also subtract. So if we subtract remember what we got when we subtracted? We got 4i. Well, let's see. Algebraically, we got 4i when we subtracted because we swapped these signs. This became a negative. This became a positive. The ones canceled. 2i plus 2i is 4i. Let's see if we can do it graphically. Well, if we were to subtract this complex number, we reverse the direction. So we go back this way. So this becomes -1 plus 2i. When we subtract it, we change these signs. So -1 plus 2i. Here's -1. Here's plus 2i. So now if we were to combine these, we can see that the imaginary parts are going to add and the real parts are going to cancel. So we can look at these as here's the 4i. And so you could look at these as vectors, where if you were to slide the origin of this vector and the terminal part being the arrow, if we were to slide this up like this and combine these two, we could say put this origin at the terminal part here, and the new terminal part becomes, if this is z, negative z2, if I call that z1 and call that z2, this becomes negative z2, that's this value. And if I combine those, then the real parts cancel and we're left with just a z3, which is just the imaginary part here, the 4 in the I direction. Make sense to everybody? Questions on that at all?
What's a vector?
I'm sorry?
What's a vector?
A vector is just another name for a complex number. It has magnitude and it has direction. Magnitude would be the length and the direction would be which way it's pointing.
Okay, thank you.
Okay, other questions before we continue? All right, let me take you through some other examples then. See if we can work some of these. If I give you 5 minus 2i, and I ask you to add that to 3 plus 3i, would you be able to do that? I mean, I can call this z1 and z2, or I can just say, here's a complex value, here's a complex value, add them. Go ahead and add them and tell me what you get. And let's get as many new volunteers as we can. We don't want just 1 or 2 people answering all the questions. Everybody should be able to participate. We're going to add the real parts and the imaginary parts, negative, positive. We're just going to end up with a I, aren't we? When we combine these, so we'll add these, we'll add those. It makes sense what we got there? Question on that? How about a 2 plus 6i, and we subtract 12 minus I. So we have a minus 12 and a positive I when we distribute this negative here into the parenthesis. And then we combine these. So we would get what? A 2 and negative 12 would be negative 10. And this is a plus. So I get 6 and a plus. 6 and 1 is 7, isn't it? Because we're adding them. 7i. Okay, so we get 10, negative 10 plus 7i. Okay, so those are some examples of additions. How about some products? So these were adds and subtract. Let's say we have a product and I have 7i times 2 minus 9i. And we're going to distribute that 7i, aren't we? So if we distribute the 7i into this binomial here, 7 times 2 is 14i, and then 7i times -9, that's going to be a negative value. Positive times a negative is a negative. 7 times 9, well, that's 63. And then I times I is I squared. And I squared was what? You remember what I squared was?
-1.
-1. So that'd be -1. We get 14i plus 63. And we want to write that in normal a plus bi form. So we'd say 63 plus 14i. That would be the conventional way of writing that. Questions on that at all? Make sense?
Yep.
Okay, we might have 5 plus 4i times 6 minus 7i. We'd want to FOIL this, wouldn't we? First times first, 5 times 6, that's 30. Outer is negative 35i. Inner is positive 24i. And last is negative 4 times 7 is 28, and that's I squared. So now we need to simplify. We always want to simplify. So we've got 30. And then we have some I terms here. 35 and 24. Looks like that's -11, isn't it? -11, and those are I's. Combine those. And then 28 is a negative 28, and an I squared is -1. So that looks like it's positive 28. So combine the 30 and the 28, and I'll get 58 minus 11i. When I take this binomial, multiply it times that binomial. Okay, questions on what we did there? Okay, let's try a division. Maybe we have 5 plus 4i, and we want to divide that by, let's just say it's 4 minus I. So we'd say, well, let's see, 5 plus 4i in the numerator, and in the denominator, 4 minus I. And that I represents a radical, doesn't it? Square root of -1. So we want to get that out of the denominator. So we're going to multiply by the conjugate, 4 plus I.
Professor,
4
could you
plus-
move the paper up a little?
Yes.
Thank you.
Okay, so here, this is the complex conjugate. Complex because it has a real and imaginary component. Conjugate because we have the opposite sign. So in the denominator, then we'll have 4 times 4 is 16. Outer and inner are going to cancel. And the last is going to be negative I squared. And I squared is -1. So that looks like it's going to be a positive 1. So that's going to be 16 plus 1 is 17, isn't it? And in the numerator, 5 plus 4i times 4 plus I. First times first is 20. Outer is 5i. Inner is 16i. And last is 4 times I squared, which is -1. So it looks like we have 20 and a -4. That's going to be 16. And then for the I component, we have 16 and 5. That's 21 of the I values. So we're going to have something that looks like that, but we want to put it in terms of A plus BI. So we could say the complex value is going to be 16 over 17 plus 21 over 17, and those are in the I direction. All right, so that's doing a division operation. Okay, questions on that at all? All right, let's see if we can solve a problem then. If you're given a problem that says x squared minus 2x plus 2, say f of x equals that, and we want to find the zeros. The zeros are where this function crosses the x-axis, isn't it? So we'd set this equal to 0 and then factor. So if we factor, you'd say, well, we could factor this thing by, let's say we've got 1 here as a leading coefficient, so that's the x and x. And over here, that's 2. That could be 1 and 2 or 2 and 1. And then we have to get a negative 2 when we add the outer and the inner. So let's see, that's x squared. To get a negative 2, these signs have to be the opposite. So let's make them the opposites. That gives us a negative 2. And then if we do outer, negative 2, inner, positive 1, that gives me a negative 1, but we're looking for a negative 2. So it looks like we can't factor this way. So if we can't factor that way, is there another way we could factor this quadratic equation here, this quadratic function? Could we use a quadratic formula? Remember what that was? Minus b plus or minus b squared minus 4ac. Remember that, all over 2a. So we'll have to go back up to this and say, well, what is a? What is b? What is c? Looks like a is going to be just 1. And b is going to be negative 2. And c is going to be regular 2, positive 2. So if we substitute that back in, we get minus b plus or minus the root of b squared, which is just going to be 4, isn't it? Minus 4 times a, which is 1, times c, which is 2, all over 2 times a, which is just 2. So we get x equals negative 2, which is positive 2, plus or minus, and that's going to be over 2. Here we have 4, and here we have negative 8. So this gives me a root of negative 4 here, doesn't it? So let's clean this up a little bit. There we go. So this says 2 plus or minus over 2. And this negative, the root of negative 4, we figured that out earlier. That was a root negative 1 times the root of 4. So that's 2 plus root of negative 1 is I. Root of 4 is 2. And that's 2. And then we can simplify. 2 over 2 is 1. 2i over 2 is just I, isn't it? And so we've got a plus and a minus here because we had that. So I'll make that a plus or minus there. So we'll say then the answer is going to be 1 plus or minus I. Okay, now if we take a look at that solution, here's the real axis, here's the imaginary axis, over 1, up 1. So if we go over 1, this value, and up 1, we end up here. And over 1 and down 1 would be here. And you'll notice that neither one of these are a solution on the real axis. We have a solution up here. So this value does not, I don't have to put in this z value here. I could just say, well, what was the solution? The solution was right here at 1 plus I and 1 minus I. Well, neither one of these solutions exist on the real number line, do they? So if we say, where does this function cross the real number line? It doesn't. Okay, it doesn't have a solution on the real number line. Make sense to everybody? Questions on that at all? Okay, that's all I was planning to cover on section 2.1. We've gone through the objectives that we had of adding, subtracting, multiplying, and dividing. So let me pick up.
I have a question.
Go right ahead.
Sorry.
Go right ahead.
Why did we use the quadratic equation?
Well, because we tried to factor and we weren't successful.
Oh, okay.
We tried to do our normal factoring where we look at the leading coefficient and say, well, that was 1, so we put an x and an x, and this was 2, which means our factors are 1 and 2. It's all they are. It's the only possibilities. But when we put these values in here, whether we put a 2 here or a 1 here, we couldn't make this work. So we couldn't factor using this method, but we can always factor using the quadratic formula, can't we? So we just plugged in values for A, B, and C, and then use that.
So I have a question also. So so the answer would be that there's no 0, or would it be 1 plus or minus I?
The answer is that there is no location where this function crosses the real axis. So you would just have to answer whatever the question asks. If it says, where does this function cross the real axis? It doesn't. It exists at 1 plus I and 1 minus I, but it never does cross this axis here.
Okay, thank you.
Yes. Now, if this value were to go away, then we'd say, well, it's out here at x equals 1, but it has a imaginary component. So the solution to this equation, when we solve it, gives us an answer of 1 plus I and 1 minus I, neither of which exist on the real axis. Okay. The second section I want to cover is quadratic functions. And what I want to be able to do for some objectives is to recognize the characteristics of parabolas. We want the characteristics of these. We want to be able to graph a parabola. We want to see if we're looking at a parabola, does it open upward? Does it open downward? If it opens upward, then we can say, well, can we find some minimum value? We can say, well, yeah, the minimum right here is at the vertex. If it opens downward like this, then we can say, is there a maximum value? And the maximum value here. So here we find a minimum. Here we find a maximum. Okay. And then we want to be able to see if we can solve some problems involving minimums and maximums. So those are going to be the objectives for the next 12 minutes, then we'll take our break. Now, if I give you the general equation, if I say y equals, let's say x squared, we'd say, well, that's a quadratic. It's a square. Its leading coefficient is 1. So there's no stretch or shrink. If that were larger than 1, we'd call that a stretch value. If it were greater than 0 but less than 1, we'd call it a shrinking value. So as if we were to just draw a parabola like that, where we go 0 and maybe over 1 and up 1, over 1 and up 1, and over 2 and up 4, because it's squared. So over 2 and up 4. So we'd say, well, here's the point 0, 0. Here's the point 1, 1. Here's the point 2 and 4. Here's the point -2, 4. Here's the point -1 and +1. So these are the points. And if you were asked to graph this, this is what I would expect you to show me. That here are the points and here are the locations. Now you notice this paper this isn't graph paper. It's just blank paper, but I'm putting 1, 2, 3, 4, 5 points, and I'm telling you what those points are, whether this is a pretty parabola or not. I'm telling you these are where the points are. So I could have set up a table of values, X and Y, and gone from -2, -1, 0, 1, and 2, and say we went from negative, or went from +4, +2. So we went -1, +1, 0, 0, +1 and 1, +2 and 4. So that's how we would get these points, by creating a table of values for X values, in this case, -2 to +2, and Y values of a +4, +4, +1, 0, and so forth. So we're just talking about quadratic functions now. Okay, so here's an example of a quadratic function. It's a parabola, and here's what it looks like. So anytime I see a function that looks like it's this form, well, I know it's a parabola. Now I can move that parabola around. I could say, well, here's my X and Y, and I want to move this parabola around. Well, I could say, well, then let Y equal some value A times X minus H quantity square plus K. I'll say, gee, what does that do? Well, this becomes, if A is greater than 1, it stretches this parabola, so that if it were 2, for instance, if this A were a 2 value, well, you'd go over 1 and up 2. So you'd say, well, I'm up here 2. So if I were to stretch it, it would go over 1 up 2. So let's say that's here. And back 1 and up 2. So maybe it's there. And then if I go over 2, well, on my original, I went up 4. Well, here I'm multiplying by 2. So now I'm going up 8. So now I'm going up much steeper. So it looks like I've got a parabola that looks like that. And that's what happens when we put a stretch value in there, in this case, A. The H value here, you'll notice what H is doing is, and H is a shifting. And that's a shift in the horizontal direction. So H and K is also a shift, but it's in the vertical direction. So if K is positive and H is positive, then I'm going to shift the vertex from here, some value to the right and some value up. So if I had the same values for that I had here, and this was just a 1, but I had an H and a K, this is all I'm doing is taking this original curve and shifting it by whatever the values of k of h and k are. If h is 2 and k is 2, I go over 2 and up 2, and then I would create the same graph located there. So my vertex would be here, go over 1 and up 1, so I've got points here, over 2 and up 4, 1, 2, 3, 4, so it roughly here and here, and I'll have a curve that looks like that. So this could be the curve with the formula y equals x minus 2 quantity square plus 2. We've taken the parent, this original function, and shifted it to the right 2 values and up 2 values, 2 units. There's 2, there's 2. Okay. So we're just moving this curve, this parabola, we're moving it with h and k values. H moving it horizontally, k moving it vertically, and then whatever the a value is here, it either stretches it, which makes it look like this, or it might shrink it, meaning that it gets flatter. It would look like that. If a were greater than 0 but less than 1, so if a is greater than 0 but less than 1, we'd have a flat curve like this. Up here we have a greater than 1, and this is a equal to 1. So we're either stretching or shrinking or just leaving it alone, just a value of 1. Okay, questions? And also keep in mind that this curve is symmetric about the y-axis. If I draw the y-axis here, these curves are all symmetric about the y-axis. Similarly here, we're symmetric about a line parallel to the y-axis because we have moved the curve off of the y-axis by putting this h value in here, which shifted it to the right. Okay. Questions? Okay. So let me see, what else do we want to, we've got about 4 minutes. Let me just take you through some examples then, and then we'll take a break. So let's take you through, say we want to graph y equals some function of x equals -2 x minus 3 square plus 8. Let's say I want to go ahead and graph that. So I could set up a table of values, couldn't I? X, Y. And if I were to graph that, well, let's see, I can immediately look at it. Well, let's start at the beginning here. We look at a function like this and say, well, what is this thing? And you look at it and you say, well, it's a quadratic. We're taking the independent variable here and we're squaring it. We're shifting it based on this value. We're shifting it vertically based on this value. This is a horizontal shift. Here's a vertical shift. And we're doing a stretch based on this value. And we're opening downward because of the negative. So I know it's a parabola. It's opening downward. It's shifted right 3, 1, 2, 3, and up 8. Here's up 8. So here's my vertex over 3, up 8. It's opening downward. So it goes down like that, and it has a stretch value of 2. It's going to basically look like this. And then I can put in some values if I want. I can say, well, let x equal 0, 1, 2, 3, 4, however far we want to go, 5, let's say. So if x is 0, -3 squared is 9, times -2 is -18, plus 8, that gives me a -10, doesn't it? If I put in a 1, I get a -2 squared is 4, 8, it's -8, plus 8, that's a 0. I put in a 2, I get a 6, put in a 3, I get an 8, put in a 4, I get a 6. I'll let you do these calculations on your own rather than taking everybody's time to do that calculation. I put in a 6, I get a negative 10. So let's see, 0, negative 10. So maybe that here, 0, negative 10 over 1, and y is 0. So it looks like we're here. 2, I'm at 6, so that's going to be here. 3 and 8, 4 at 6, that's here. 5 is 0, that's there. 6, negative 10, that's down in here. So it looks like I have something that looks sort of like that. And remember, I always want you to label your points. So here's 0, negative 10, 1 and 0, 2 and 6, 3 and 8, because these points don't have any meaning unless I label them. 4 and 6, 5 and 0, 6 and negative 10. And I will highlight these just to make sure that we know what those are. So now I'm showing my points here that I've got from my table of values. So here's my table of values that I use to find the points. And I plot the points. And then after I plot the points, then I connect the points with a smooth curve. And it looks sort of like that. And I could say, what's the domain and range? And you'd say, let's see, what do we think the domain is on this function, negative 2 times the quantity x minus 3 quantity squared plus 8? What would the domain be on that? Anybody? Well, this extends as far as we want, doesn't it? We could go negative, positive. We're just going to keep going. So the domain is going to be from negative infinity to positive infinity, isn't it? And how about the range? Well, we're going to peak here at y equals 8, and we're going to include that 8. But the minimum value, well, that's going to be negative infinity again, isn't it? We don't include that. So we could say, well, here's the graph, here's the function, here's the table of values that we got our points, plotted them, and then we got our domain and our range. Okay, we might, I don't know, maybe there are other questions we could ask, but we've pretty much identified what this graph looks like. Okay, I have 4:02. How much time do you want for break? 5 minutes or 10 minutes, or how much time would you like?
5 minutes.
5 minutes, that's fine. So we'll see you guys about 4:07, somewhere around 4:07. Okay, we'll come back, and then if you've got questions, please bring them up. Good work, everybody. Okay, are we back? Questions have come up on anything we've covered so far? No questions? Okay. Let's take a look at some problems then. If I asked you to graph could we do that? Could we graph that equation? If so, what would it look like? Negative x squared plus 4x plus 1. And we want to locate the vertex. And maybe the x-intercepts. And maybe the y-intercept. And then maybe plot some points. And graph. Would we be able to do that with that function right there? Do we know enough to do that? Do we know an easy way to find the vertex? Well, you may have seen a situation where the vertex, at least the x coordinate of the vertex, is equal to negative b over 4a. That's an equation. I'm not going to derive it, and I'm not going to ask you to derive it, but we could. But the x component of the vertex would be negative b over 4a, where in this case, a equals negative 1, b equals 4, and c equals 1. Negative 1, 4, and 1. So using those values, negative b, the negative 4, over 2 times a, which would be negative 2, wouldn't it? So that'd give me just a 2. So that says that the x component of the vertex, negative b over, it should be 2a, not 4a, negative b over 2a. And here's my origin. So I'm saying if I go out here at 2, 2, 3, 4, 5. So here's 2. So somewhere on this line is going to be my vertex. And if I want the y-intercept, I could say, well, let's put into the equation y equals negative x is 2 squared plus 4 times 2 plus 1. And let's resolve that. So there's an 8. And here's a negative 4. Here's a positive 1. So that's 8 and 1 is 9 minus 4. That's a 5. So that says the vertex is going to have a y value of 5 and an x value of 2. So let me just go up this way. And we'll go up 1, 2, 3, 4, 5. So at this point here, at 2 and 5, I'll say that's my vertex. It's a quadratic equation, meaning it's a parabola. It's opening downward because of this negative. And the vertex we located at negative b over 2a. So I'm going to put it right there. And if I want to look at the x-intercepts, well, maybe take the y-intercept first, because as we come down, we're going to hit the y-axis first. So when we hit the y-axis, x is what? X is 0 at the y-axis. We're not, when we're going x in this direction, x going out this way, we're not going to hit the y-axis, but x coming back here, when x is 0, we're going to hit the y-axis, aren't we? So we could substitute a 0 for x here and here, and we're left with 1. So when x is 0, y is 1. So apparently we're here at 0 and 1. We have a point here. So we're going to come down like that. And we're also going to be symmetric about this vertical line here. So at 1, we were over 2. So apparently over 2 more, we're going to be, apparently we're going to have a point here because it is symmetric. So apparently we're going to have a point here at 4 and 1. And what else can we have? Let's see. We want, well, we might want the x-intercepts. We got the y-intercept, we've got the vertex, the x-intercept. Well, the x-intercept is when y is 0. So we'd say negative 4x squared plus 4x plus 1, and we set that equal to 0. And we say, well, let's see, let's solve this, and we can try and factor it, and we're going to find out that that didn't work very well. You can try that on your own, but I'm going to give you a hint and say, let's solve this using the quadratic formula. Right, minus b plus or minus b squared minus 4ac all over 2a. So why don't you solve that and open up your mic and tell me what you get for x when you solve this. Get everybody involved here. What'd you guys get? Did you get that? Negative 4 plus or minus, I guess we can make that a root 4, root 5 over negative 2.
Professor, I got negative 4 plus minus square root of 12, not 20. I'm not sure if I did it wrong.
Did you get this?
No, I got square root of 12 instead of square root of 20.
Well, b squared would be 16, wouldn't it? Minus 4 times negative 1 times positive 1, so that's just 4, so that's plus 4.
Oh, okay.
And 16 would give me a 20.
Okay, I got it.
And we'll factor that into 4 and 5. 4 we can take the square root of, so that's negative 4 plus or minus 2 root 5 over negative 2. So here we have negative 4 over negative 2, and we have plus or minus root 2 root 5 over negative 2. So this will be a 2 plus or minus root 5, it looks like, because these 2's will cancel. So we'll have x can be at 2 plus or minus root 5. Okay, so we would say then 2 plus or minus, let's see, 2 minus root 5, what is that? 2 minus root 5 is negative 0.23. So it looks like it's going to be less than 1. So somewhere out in here, so negative 0. Let's say round it to 24. Y is 0, so we'll have that point, this point. And then if we have a 2 plus root 5, we would be at 4.24, so it's 4 somewhere out in here. So 4.24 and 0. So if I highlight these, 4, 2, 4 and 0, 4 and 1, 2 and 5, 0 and 1, negative 2, 4, and I look at my points here, and I'll draw this graph sort of like that and like that. I think we're going to look approximately like this. And if I wanted exact values, here are the exact x-intercept. If I'm looking for approximate, then I would say x is approximately out here. So this is approximate. Okay, at this negative 0.24. And we also have one here at approximately 4.24. Okay, so we went through the analysis of this equation. And the only thing you were given was the fact that the vertex is here. And I'm not asking you to develop that. You can develop that, but what you end up doing is simply saying, if this is the x version or the x equation for the vertex, then I just have to put this value into f of x to find the y value. So I'd say f at negative b over 2a would give me the value up here. I could do that if I wanted to find this 5 value here. So here's the x value. I'll highlight that. Here's the x value, which is negative b over 2a. And the y value is when you evaluate this function at this location. And we said the location was 2. So that's f evaluated at 2. And we did that substitution here. And we ended up with a 5. So we said, well, 2 and 5 then would be the vertex. Okay, so having found the vertex, to find the x-intercepts, we just used the quadratic formula, which was this guy here. We could try and factor it, but it turns out we're not going to be able to factor that. Y-intercept, we can find that when x is 0, so we can find that without a problem. And we get 0 and 1, and we know that this is symmetric, so we could draw a horizontal line and go over the same number of units, which is 2. So we go over 4 and up 1, so we have those points. Axis of symmetry, we know it's parallel to the y-axis, so the axis of symmetry is at x equals 2. This vertical line at x equals 2 is the axis of symmetry. Okay, so it looks like we found out about everything we need to find out about that equation. Questions at all? Okay, let's see. Maybe we'll do one more and then we'll go on to the next section here. Let's see here. if I say I give you 120 feet of fencing. So let me get a new piece of paper here so it's not. Okay, I'm gonna enclose an area that's a rectangle. And I have a length and a width and a length and a width. And I know that the perimeter of this rectangle is 2 lengths plus 2 widths. We know that's true, don't we? And we know the area of this rectangle is the length times width. Okay. And I'm going to say the perimeter I'm going to give you is 120 feet. Here's the perimeter of this rectangle. And what I'm going to ask you to find then is the value of L and the value of W that maximizes this area, given that we have this. Okay, so we understand what the question is? Okay, so let's see if we can do it. So we have 120. Well, we have this equation, so we could say 120 equals 2L plus 2W. That's one equation. But in order to solve for length and width, we're going to need 2 equations, aren't we? Well, we know the area is length times width. Can we solve this equation for length in terms of width? That is to say, solve this equation for L. Well, let's see. If we divide through by 2, we get 120 divided by 2. That's 60, isn't it? Equals L plus W, or L as a function of W is 60 minus W, isn't it? So now we have the perimeter and we have length as a function of width. And we can say, well, if I'm looking for area, if I want to maximize the area, that's going to be length times width. The length is 60 minus W, and the width is just W. So the area, so now I guess I could say the area as a function of W equals 60 minus W times W. Let's just distribute the W. We'll get area as a function of width is equal to 60 W minus W squared. And now we can look at this and say, well, this is a quadratic squared. So it's a parabola. It either opens upward or it opens downward. This indicates that it's opening downward. So we can get rid of this. Say it is a parabola doing that, which is what we would expect, because if we're looking to find the maximum area, we want to find the max, then we're going to want to be at this location on this curve that we have here. So here's the equation. What we want to do is find the location in the W direction that maximizes this area. So here's area as a function of W, and here's W. So we have to find the maximum value here. And that has a vertex at W, and the vertical is going to be the A evaluated at W. It's going to be the area. So if I can find the maximum point of this curve, it looks like I would be there. Okay. So earlier we said that the horizontal component of the vertex we said was x. In this case, we'll call it w. And we'll say that's negative b over 2a. So a in this case is negative 1. B is 60, and C looks like it's 0, doesn't it? So negative b would be negative 60 over 2 times negative 1 would be negative 2. So it looks like that's going to be 30. So w is 30. So when w equals 30, we're out here at the maximum area. And but we weren't asked to find max area. We were asked to find what would the length be to find maximum area. What would the dimensions be? So we want to solve this equation up here for L. So we can say L equals 60 minus W, which is 60 minus 30, which is 30. So this says if L is 30 and W is 30, we're going to maximize this area. So the area is 30 times 30, or the area is going to be 900. 900, and that's going to be square feet, isn't it? These are dimensions in feet. So to get a maximum area of 120 feet on the perimeter, we would have 30 feet on each side, which would give us a maximum area of 900. And we solve that by creating the equation that we needed to find the maximum of, which was this one here. We were able to develop that equation, and then finding that this is a parabola opening downward, we can find the maximum and find out what the width is, and then substitute and find the length.
Could you please show again how you found the length?
The length? Yes. I said the perimeter initially was 2L plus 2W, which is 120. So what I did is I solved this for the length. Did that down here. So I divided everything by 2 to get just the length. So 120 divided by 2 is 60. 2L divided by 2 is L. 2W divided by 2 is just W. Solving for L, I subtract W from each side, and I get L equals 60 minus W, which
I'm
is
sorry,
this.
I meant how you got L equals 30.
Well, if I solved for W down here, didn't I?
Yeah.
And I plug this W right here. L equals 60 minus whatever W is, and W is 30. So 60 minus 30 is still 30. So that gives me the L is 30, W is 30.
Okay, but I tried. Okay, so I think. Okay, I got it. Thank you.
Sure. Other questions? All right, I think I'm going to stop with that section so that we have time to go over the third section. So let me gather my work here and get out the next section. Okay, the next section, 2.3, is polynomial functions and their graphs. Now, this one is a kind of an interesting section because what we're going to end up doing here for some of our objectives, we want to first of all be able to identify polynomial functions. That is to say, what do they look like in general? How do we know if something is a polynomial function or not? And then we want to be able to find the characteristics of their graphs. And there are times when we want to determine the end behavior. The end behavior are at the extremes of a positive or negative large value for x, the independent variable. So we want to take x, make it very large positive, take x, make it very large negative, and see what these polynomial graphs look like. We might want to factor to find where they cross the x-axis, that is to say the zeros. The zeros are sometimes called the roots and sometimes called the solutions. So whether you hear roots or solutions or zeros, we're asking, where does this graph cross the x-axis? Might cross here, might cross here, might cross here. So if I ask you for the zeros of something that looked like this, you'd say, well, the zeros are here, here, and here, or the roots, or the solutions. We're going to introduce something called the intermediate value theorem, and we'll show you how that's defined and what we can use it for. And then we might want to determine the number of turning points. So if a graph looks like this, and we say, well, we're heading up this way, and we turn here, and we head down this way, and we turn here, and we head back up. The number of turning points in this case is 2. Okay, and we're going to see how we find out how we can calculate the number of turning points. Then we might want to maybe create a table of values, plot points, and graph. So those are some of the things that we might want to do as we look at polynomial functions. So I'm going to start out by saying, if we're looking at a polynomial function, we're going to say it's of the form some function of x equals, and we'll create a general formula first. So we'll say, well, it could have a leading coefficient, let's say a, and then times our independent variable, and the independent variable might have some exponent, whatever that value is. And we'll say then that the leading coefficient is some value n and it has some exponent. And then the next one down would be x and a lower exponent, and this might be a to the n minus 1 plus, and these are going to continue to decrease until we get a to the 1, x to the exponent of 1. We keep reducing these exponents until we get to 1 plus a sub 0 times x, and this might be to the 0. So x to the 0 is 1, isn't it? So we could just list this as the a to 0 if we want. So when we look at this as the definition of a polynomial function, the end behavior we can determine by looking at this leading value here. We have a leading coefficient here, and it turns out then that as the x value gets larger and larger and larger, whether positive or negative, that these values play less and less of a role into what's happening with this function, whether it's increasing or decreasing. Because as this gets large, this value it overwhelms any of these values down here. So really this first term is what determines the end behavior. So we've got some general rules we can use to look at end behavior. And we can say for n, this value here, being odd being, let's say, 1, 3, 5, and so forth. So if n is odd, and we might have n even, 2, 4, 6, so forth. So this n value, this exponent might be odd, might be even, and it might be, we might have an a value here in the front. We might have an a sub n that's positive, that is, it's greater than 0, which we'll call positive, or it might be less than 0, which we'll call negative. And similarly over here, a greater than 0, positive, and a less than 0, negative. And so now what I can do is look at each of these situations and say, what does the end value of this polynomial look like when x gets very large or x gets very small in the negative direction? Very large in the negative direction, or you could call it a small value, but it's a large negative value. So we're looking at x positive, x negative. As x continues to go to the left, x continues to go to the right. What these show us then is what this curve, what this polynomial is going to look like as x gets very large and positive. And if this is odd, if the exponent is odd, and this is the leading coefficient is positive, then we're going to have a curve that looks like that, as long as this is odd. So if that were 1, it would just be a straight line that looked like that. Okay, and as we start adding exponents 3, 5, 7, 9, we start developing this kind of a curve, and I'll show you some examples of that in a minute. Okay, so again, if we had y equals x to the 1 look like a straight line, we might have y equals x to the 3 might look like this. And then we might have y equals x to the 5 minus x to the 3 minus x. And we might have something that, who knows, it might have even more waves down here as we continue to add values. The ends will still look like this. The ends will be going up as x gets large positive and going down as x gets large negative. For odd and a is positive, leading coefficient positive. Okay, so we want to remember what that looks like. Here we have a is negative. This leading coefficient is negative. Everything is the same, except now we're going upper left to lower right. Instead of going up, we're going down. And we might look like that. Or we might look like that, depending. But that's all we did, is switch the value here to a negative value from a positive value. And we flip this curve around. Now, if we have a even, so this was odd, here even. And you might be able to guess what's going to happen if it's even. For squaring it, well, we take a positive number and square it, we get a positive number. Take a negative number and square it, we still get a positive number. So whether we get a large negative or large positive, as long as it's even, 2, 4, 6, whatever, then our end behavior is going upwards. And as you might guess, if A is negative, it's the same thing, but reversed. We're going downwards. Okay, so here we might have y equals x squared. We'd have something that goes up on the end behavior. If I have y equals 2x to the fourth minus 4x squared, for instance, we'd look more like this. And over here, we might have y equals negative 2x to the 4 plus 4x squared. And we'd be negative here, meaning we're going down. And keep in mind, it's always this leading term that's determining it for us. This is even, so we're going in the same direction. This is positive, so we're going upward. Over here, this is even, so we're going in the same direction for the end behavior. And this is negative, so we're going downward. Okay, so that's the general theory of what we're doing. Now we're going to take a look at some actual examples. Okay, but before I do that, I'll ask for any questions that you might have. Okay, let's say we have, let's say you're given f of x equals x to the 4 minus 4x squared. And you're asked for use the leading coefficient test to determine end behavior. End behavior being x is large positive or x large negative. So as x gets very large, what's going to happen? And leading coefficient test says we're going to look at just the first term. We're going to look at the exponent. Exponent, is this exponent even or odd?
Even.
Even.
It's even. And the leading coefficient, positive or negative? Positive, isn't it? Okay, so if we look up here at our general discussion up here, we said, well, if it's even, we're over here, and positive, we're here. So we would expect this curve in the endpoints to look going upward to the left and upward to the right. Does that make sense to everybody? Let's see, do I have a calculator that I can put that into and see if that works? Let's see, if I say y equals x to the 4 minus 4x squared, and then I would need a window here. I don't know what size window I need here. Let's just try something and see what happens. Okay, I put in y equals x to the 4 minus 4x squared here. And I set up a window of x going from -5 to +5 in increments of 1, and y going from -10 to +10 in increments of 1. And then I'm going to graph that and see what it looks like. And based on our analysis, we said it was even and positive, so we expected it to look like this. So when I hit graph, I got something that looked like that. So it goes upwards to the left, upwards to the right, and does some movement down in here. Okay, see how that's working. So if you were asked, what's the end behavior using the leading coefficient test, you would say, well, here's the first value, here's the leading coefficient, here's the exponent. I would expect even and positive to be looking like that. Make sense to everybody? Questions? Okay, let me just take another one then. Use the leading coefficient test, same as we did before. And let's say f of x equals maybe something a little different. 2x cubed times x minus 1 times x plus 5. And if we look at that and say, well, let's see, what am I going to do to determine end behavior here? Well, I want to find the exponent value. As I did here, I had an exponent of 4. I was adding these values. Well, with an exponent down here, I've got 3, and then I'm multiplying this independent variable. So this has an exponent of 1, and that has an exponent of 1, so 3. If I have a common base, I add the exponent. So now I get an exponent of 5, don't I? The exponent of 5, that's odd. So I'm over here at the odd. And then I'm saying, do we have something that is the initial value positive or negative? And we're going to say, well, this is positive, isn't it? This leading coefficient is positive. So if it's odd and positive, I would expect it to go from lower left to upper right. I would expect it to look in this fashion here. Okay, now I can try and put this into my calculator here and see what I get. So I have 2x cubed times x minus 1 times x plus 5. So 2x cubed, x minus 1, x plus 5. And I don't know whether my window is going to be large enough or not here. Let's make it a little bit larger. Let's say -10 to 10. We'll leave y at 10 and 10 and just see if we can find out something here. So I'll hit graph, and I get a graph looks like that. And it looks like my window wasn't quite large enough to show everything. So it looks like I need more in the y direction. So I don't know how big I need in the y direction, but let's say I go to 100 and 100 in increments of, let's say, 20 and graph that. Now it's even longer than that. Okay. So let's say it's 500. Okay, we're starting to get there. And so we do have a curve that we can expand our window, but where you can see we have a curve that goes from lower left to upper right. We can find out more variables on this, but we were able to determine that by doing our testing from this set of general descriptions here, where we have the exponent is odd or even, positive or negative, and here's what we would expect to look like. So if you're given the question, use a leading coefficient test to determine the end behavior of this, you could say, well, that's pretty simple. This is 3, which is odd, and this 2, which is positive. Odd and positive looks like that, and very quickly I can say that it's going to look from lower left to upper right. Questions? Okay, now what I would like to do now is new concept. Let's say we have a function that looks like f of x equals x cubed plus 2x squared minus 4x minus 8. And I want to find, say I want to find zeros. Maybe end behavior. So let's see what we can do to solve that. Well, this is 1, 2, 3, 4 terms polynomial. Well, we could maybe factor this by grouping. So we can take the first two terms, x cubed plus x squared, and the second two terms, negative 4x minus 8, and see if we can factor those. Well, it looks like we can take an x squared out of here. So x squared times, take an x squared out of here, that's x plus 1, it looks like, huh? Does that look like what we're going to be there? X squared, oh, that's a 2 out here. You guys got to catch me on this. This is a 2. We have a 2 here. So this is going to be plus 2, isn't it? So if I distribute this x squared, I get x squared times x is x cubed, which is this value. X squared times 2 is 2x squared, which is this value. Okay, that looks good. And for here, I can take out a 4. So if I take out, well, I could take out a negative 4, I guess. Minus 4 times x, that's an 8, so plus 2. Negative 4 times x is negative 4x. Negative 4 times positive 2 is negative 8. So that works. So I factor by grouping. And now I've got x squared minus 4 and x plus 2. So it looks like x squared minus 4 and x plus 2. And if I'm looking for zeros, then I set this y equals some function of x equals this. I set that equal to 0, don't I? And then solve. So x squared minus 4 equals 0 and x plus 2 equals 0. Here x equals negative 2. Here x squared equals 4, or x equals plus or minus 2. Take the root of each side, x and plus or minus 2. So now if we were to graph this on the real number line, we have a solution at x equals negative 2. Here's negative 2, here's positive 2. So we have a solution here. And we have a solution at positive 2, which is here. And we have another solution at negative 2. So this is called a multiplicity, because we have two solutions at negative 2. We have this negative 2 and we have this negative 2. And for a multiplicity, when we have an even multiplicity, it says we are going to hit this real number line, this positive x-axis, and I'll just call it x. And we're going to reflect, or I guess we could just say reflect, from the x-axis. We're either going to come down and go back up, or we're going to go up and go back down at this location, because we have a square here. If we have, so we have a exponent that's an even value. Here we have an exponent that's an odd value. Exponent that's an odd value, we're going to cross the x-axis. So if we cross the x-axis and we know we're going to look like something that looks like that, then we're going to say, well, to look like that, I can put that point at the x-axis here. So we're going to come up, we're going to come down, and then somewhere we're going to start going back up and cross this point at 2 and 0, and cross this point at negative 2 and 0. And because we had two of those, that is to say we're squared, a square looks like a parabola, doesn't it? So this is a parabola inverted this way, because we're going from lower left to upper right. Okay, lower left to upper right, because of what we started with. We were odd and positive. And if we look at odd and positive, we go lower left, upper right. Let me just bring that back again. So here's odd and positive, And we have a curve that looks like this. And that's what we had here. And so we have a curve that looks like that. And at this -2 point is where we reflect off of the x-axis. Now we haven't asked for other points here. We could ask to solve for other values here, but we wanted to know where did it cross the x-axis? What was generally the shape of the curve? Okay, and we found zeros then here. We can call them zeros. We can call them roots. We can call them solutions. And if we're asked for multiplicity, said, well, because we had a square here, we had a multiplicity. We had two values that were located at -2. Okay, questions?
So what does the multiplicity represent? I didn't get that.
You'll have to speak a little louder. The multiplicity of what?
So I didn't get what the multiplicity represents.
Oh, it represents the fact that we're going to turn around at this location of the zero. If it's an odd multiplicity, we're going to cross the axis. If it's an even multiplicity, we're going to be reflecting or turn around at the zero location.
Okay, thank you.
Sure. Other questions? Here's our graph here. Goes this direction and this direction. Okay. And where we have an even multiplicity, we're turning around. Other questions? Okay, let's try another one. Well, let's see, it's 5 o'clock. Let me try a new concept. Make sure we get through all the concepts and we can come back for others if we have time. Let's, given a function, f of x equals 3x cubed minus 10x plus 9. And the question is, do we have a real zero? Is there a zero between x equals -3 and x equals -2? So we might graph this thing, say, well, using our leading coefficient test, this is odd and this is positive. And we bring back our curve here and we say, oh, the curve for odd and positive looks lower left, upper right. So it looks like this curve might look like that based on coefficient test. And we're looking between -3 and -2. So negative values be out here. So maybe 3 and 2, let's call this -1, -2, and -3. So here's -2, here's -3, -1. So here's the point we're looking at right here, a point between -2 and 3. And the question is, does this curve cross the x-axis between -2 and -3? Is there a zero between that? So we can plug in -3. So f evaluated at -3, and we'll evaluate f at -2. So f at -3 is 3, -3 cubed, -10, -3 plus 9. And here we have 3 times -2 cubed minus 10, -2 plus 9. So we need to evaluate those and see what we get. So can anybody evaluate those and see what values we get? -3 cubed, -10, -3 plus 9. So that's negative 27 times 3. That's going to be a negative. And here is a positive 30 and a positive 9. What did we get when we solved that? So negative 3 cubed, negative 3 gives me a negative 27 times 3. 3 times negative 27. Looks like that's negative 81. And then 10 times 3, that's going to be positive 30, positive 9. So 81 minus 39. 81 plus 39 gives me, oh, I've got to do the right value here. Negative 81 plus 39. Did you get negative 42?
Yes. And then for the second one, I got positive 5.
Positive 5. Okay. So if we have a negative 42 at negative 3, we're down in here. Negative 3, negative 42. And at negative 2, we were at 5, so we're on the upside. So that indicates that since we have a continuous curve, and it's at negative 3, it's negative 42, and at negative 2, it's positive 5, it indicates we've crossed the x-axis here at some point, doesn't it?
Could you please, sorry, it's hard to kind of see the answers. What was the answer for, okay, thank you.
Okay. All right, so because we have a sign change that says we have a real 0 between negative 3 and negative 2. Okay, that makes sense to everybody what we did there?
Sorry, I didn't get that. How did we determine whether there was a 0 between those 2 points?
Who wants to take us through that?
I mean, I understand how you got negative 2 and 5 and negative 3 and negative 42, but I don't understand how that proves whether there's a 0 between or not.
Well, we said this is a continuous function that's shaped like this, goes from lower left to upper right. We got that by looking up here because it's a continuous function. And if we go 1, 2, 3, and down 42, negative 3, negative 42, and negative 2. So here's negative 3, here's negative 2. So we have a point here. Here's negative 2, and at 2, we're at up 5.
I
So
can't
here's-
share screen, Professor. Thank you.
All right, so here we're at negative 2 and 5. Here we're at negative 3, negative 42. We have a continuous curve that looks like this that goes from here to here. And if we draw a continuous line from there to there, it's going to go like that, won't it?
Oh, okay, I see. Thank you.
And it crosses the x-axis here. Okay, make sense to everybody? Questions? Okay. I don't think I have any new concepts for you. I think what I'll do is just stay on the air here and take any additional questions you might have on any of the sections that we covered today. Let's see, it's 5:08, almost 5:09. So it looks like we're pretty much, well, actually, I guess we are. We only took a 5-minute break, didn't we? So I guess we were done at 5:05, sorry. So we're done as far as class goes. You made it through the entire class. We covered sections 2.1, 2.2, and 2.3. Hopefully everybody will have completed the chapter 1 test, and we'll review that on Monday is my hope. Okay. I'll stay online for any questions in case you have any. Good work, everybody. So class is over.
Thank you.
Thank you, Professor.